Hello, this is first question. An isotope of astatine has a symbol At213 upon 85. Which row of the table shows the number of protons and the number of neutrons? So you can easily see that 85 is the number of protons. And if you need to get the number of neutrons, you just need to take away 85 from the atomic mass, and that should be 213 minus 85, meaning thereby it comes out to be something like 128. So that is why the answer is going to be something like B, right? And now we have got this question number 2. And in the question number 2, the capacitor is charging. A graph of the potential difference against the charge is shown. And you have got the potential difference and the charge itself, right? So which of the following gives the capacitance of the capacitor? Now, if you remember the formula that Q is equals to CV, so C has to be Q upon V, right? C has to be Q upon V. But if you talk about the gradient of this graph, that has to be the y component upon the x component, meaning thereby it must be delta V upon delta Q. That is going to be the gradient. So what is going to give you the capacitance? It must be the reciprocal of this thing. That has to be Q upon V. So what does that mean? That the reciprocal or the inverse of the gradient of this graph going to give you the capacitance, keeping this formula in mind. So that is why I'm going to go with the inverse of the gradient of the line, right? This one. Now, distance between a charge and a proton. And the electric field strength due to the proton is something like 0.77 newtons per coulomb. So everybody knows that the formula of electric field strength is F upon the test charge, the Q naught. And the force according to the Coulomb's law is something like 1 upon 4 pi permittivity of free space Q times Q naught divided by R square whole divided by Q naught. I'm going to cancel out this Q naught with Q naught, and I'll end up having E is equals to 1 upon 4 pi permittivity of free space Q upon R square, right? I'm looking for R square. I'm going to just pull that R over there, and R square comes out to be 1 upon 4 pi permittivity of free space Q upon E. I'm going to take the square root and I can have the final answer as well. And that must be R is equals to the square root of 1 upon 4 pi permittivity Q upon E, right? So now by just plugging the values in, you've got the charge, and the charge has to be 1.6 times 10 to the power of negative 19 divided by 4 pi. The permittivity of free space has to be 8.85 times 10 raised to the power of something like negative 11, I'd say, right? So I'm just going to go with negative 11 times the electric field strength of the charge of electric field strength is 0.77. So that is why, all of these things is given by the option number. Well, there is a negative one, which might be a misprint, right? So that is why I'm going to go with the option number B. Now you have got this question number 4. In the upper atmosphere, high energy cosmic rays collide with the molecules of air to produce muons, right? The cosmic rays are colliding and they're going to produce muons. The average speed of these muons is V. The average lifetime of the muons is greater than the average lifetime of the stationary muons, right? So these are the muons which are being produced in the upper atmosphere, right? Which of the following gives the reason for the increase in the average lifetime, right? Since they are colliding, they are being produced as a result of the collision of the cosmic rays, and in the upper atmosphere where there would not be any sort of air resistance. That is why they do have a higher average lifetime as compared to the stationary muons, because when they're going to move after the production, they might be moving with the speed of light. Not with the speed of light, you can say approximately equal to the speed of light. That is why, this cannot be the answer. This cannot be the answer. Exactly equal to is not possible, right? So I'm just going to go with C. These some sort of a mouse species denote almost equal to, right? So V should almost be equal to. That is why they would be having a higher average lifetime. Now you've got this question number 5. In a large angle alpha scattering experiment, alpha particles are directed at a thin metal foil. The alpha particles were then detected at 4 positions, right? The alpha particles are going to be detected at the 4 positions, right? You can have the W's one, you can have the X ones, you can have the Y ones, and you can have the Z ones as well, right? So they're just asking us, that where were the most of the alpha particles detected, right? You need to, they're just going to talk you that from where the most of the alpha particles would be detected. If you could remember, this is going to be a metallic foil, right? And you have got a nucleus right in between them. So you've got an alpha particles bombarded over it. So remember that there is no enough, 99% of the space inside an atom is empty. And if 99% of the space inside an atom is empty, there are very less chances that alpha particles would be diverted somewhere else, right? I'm pretty sure that they're going to get back to X, right? Some of them going to get back to Z. Some of them going to get to W as well. But most of the alpha particles would be hitting straight the point Y, because most of the space in atom is empty and alpha particle would pass through the gold foil without any uh, diversion, right? So that is why I'm going to go with option number C. And then I've got this question number 6. In an electron gun, a current heats a metal filament to release electrons. So remember that whenever a metal emits electron upon heating, whenever you're going to heat it up, they're going to release some sort of electron. This process is known as thermionic emission. Therm for the heat, ionic for the charge release, and that is why this is a very important process, thermionic emission. An electron and a positron collide and annihilate, producing two photons, right? Producing two photons. Which of the following is the energy in joules of one of these photons? The one of these photons is important. If you're going to calculate the energy, the photons, since they are released as a result of the collision with an electron, and so you need to use the mass of an electron because there must be a mass conservation over here. Mass of the electron, you need to remember, minus 31 times the c square, mc square, right? So 3 times 10 raised to the power of 8 square. That is why I'm going to go with the option number A. And which formula I've used? I've used E is equals to mc square. Now you've got this question number 8. In a high energy collisions, electrons are used to investigate the structure of nucleons, right? In a high energy collisions, you can talk about the structure of nucleons. Which of the following is the reason that why the electron need a very high energy? So we just need to talk about that in a high energy collision, electron would be used to investigate the structure of nucleons. And if electrons are used to investigate the structure of nucleons, we just need to talk about that why the electrons need a very high energy, right? So high energy is needed because whenever the electron going to collide with another atom, it must create some sort of new particles, right? That is why I'm going to go with option A. This question is important, so I'm going to talk about the B, C, D as well. So the collisions between electron and nucleons are elastic. Remember that to talk about the structure of nucleons, whether the collision is elastic or inelastic, that doesn't uh, make sense. So the electron have a large wavelength. Well, electron probably would be having a very small wavelength because there is a high energy collision. So this is mathematically, logically wrong, right? I'm not going to go with B. I'm not going to go with C. So the quark is knocked out of the nucleon. Well, you must be specified which quark you're talking about. There must be many quarks emitting out of the nucleus when a high energy collision is taking place. So because the nucleon got proton and a neutron as well, both of them got quarks. He's not specified. So I'm not going to go with option number D as well, right? Then I've got this question number 9. You've got a fission reaction and a nucleus is splitting into a nucleus S and a nucleus T and several neutrons. S and T have the same kinetic energy. So they do have the same kinetic energy. T has twice the mass of S, right? Which of the following is the ratio of momentum of T divided by the momentum of S? So if you talk about the formula, the kinetic energy is basically the square of momentum divided by 2m, right? Square of momentum divided by 2m. So if you're going to talk about the momentum from here, the momentum square would be equal to 2m times the kinetic energy. Any momentum of any object should be the square root of 2m ek, right? Now I'm just going to plug in momentum of T, right? T has twice the mass. If it has twice the mass, I'm going to write it down something like 2m times ek as well, right? And I'm going to divide it down by 2m ek, right? So then I'm just going to cancel things down. And after cancellation, I would be having 2m cancel out by 2m, ek cancel out by ek. I know you'll be probably will be worried about the square root, but remember that since they are both getting divided, right? You can write them in a single square root and then cancel them out as well. So finally, I'll be having something like to cheer about square root of 2. That is why the C is going to be the right answer. Similarly, I've got this question number 10, very technical question. You've got a model aeroplane. F and G are two positions of the model aeroplane. The velocity of F is Vf and the velocity of G is Vg as shown, right? You've got these velocities. This is going to be the final velocity, strictly speaking. This is going to be the initial velocity, right? As the model of aeroplane moves from F to G, the change in velocity is delta V. Correct vector diagram for this situation, right? If you're looking for delta V, remember that delta V is the resultant of Vg minus Vf, right? So I'm going to add both these vectors down. So first of all, I've got Vg. I'm going to somehow draw Vg something like this, right? This is coming out to be Vg. And then I've got negative Vf. So if positive Vf is over here, the negative Vf might be in this opposite direction, right? So I'm going to join the head of this Vf with the tail of this Vf with the head of Vg, and that would be something like this. That is going to be negative Vf. And the resultant vector, remember that the resultant vector is going to be towards the tail of the last vector, right? So that is why I'm going to go with this thing. Now you can consider which option feels like somehow like this. So, you've got these things and this ones as well. So I think, I've just messed up. The resultant vector must be towards the head of the last vector. Sorry. Yeah. The resultant vector, as per the head to tail rule, must be towards the head of the last vector. So only C makes sense, right? That is why I'm going to go with the option number C. So that is how we would be talking about all these multiple choices. Now we're going to get to the questions. So in the question number 11, you have got a proton enters the magnetic field as shown, right? Something like this. The proton experiences a force. You've got the force as well. And we need to calculate the speed of the proton, and the maximum flux density is, you've got this thing as well. So the force acting on a charge inside a magnetic field has to be V, Q, B sine theta. I'm going to plug in the values. The force has to be 6.5 times 10 raised to the power of negative 30. And then I've got the velocity. I'm going to, since I'm looking for the speed, I'm going to keep it as it is. And since I've got a proton, the charge on a proton is 1.6 times 10 raised to the power of negative 19. And the magnetic flux density is going to be 0.52 times by sine 90. Because you can see that the proton is subtended at an angle 90 degree to the field. So by solving it down, I would be having the final velocity, and that should be 7.8 times 10 raised to the power of 6 meters per second, right? So that is how I'm going to talk about their speed. Now in the B part, draw on the diagram above the path of the proton in the magnetic field, meaning the path which is going to be followed. So, we just need to apply the Fleming's left-hand rule over here. You can see that the proton is moving in this direction, so take the direction of current to be like this, right? Magnetic field is something like out of the paper, right? So, you just need to use FBI. And if you're using FBI, your middle finger should be towards right. Your, your first finger, your index finger should be up. And you can see that the force is acting and somehow in this direction, right? Downward. So what does that mean? That this is the path of the proton, and the proton must be following a somehow like a clockwise curve towards the bottom, right? So yeah, that is how we're going to take this thing, right? This is just about, Fleming's left-hand rule. Now we've got this question number 13, and a student is investigating the collisions using the 3 spheres, right? And we've got a sphere like 35 grams, which is striking into 2 equal masses, which is 37 grams. So this has to be something like 0.035, and each mass of these balls has to be 0.037, 0.037, right? So you've got these masses, and initially they are stationary. During the collision, the rolling sphere was brought to rest. After the collision, the velocity of this sphere going to be 0. And these started moving with a velocity of 0.21 meters per second. We need to determine an angle theta, right? So first of all, I'm just going to calculate the initial momentum. The initial momentum would be, the momentum of this sphere. That's going to be 0.035 times 0.40. And then I've got the initial momentum, and that comes out to be something like, whatever it is, we're going to calculate that. And then I'm going to calculate the momentum, plus 0 as well over here, because these are the stationary spheres. Now I'm going to calculate the final momentum. The momentum of this ball going to be 0 plus. You've got two balls, and you've got the masses, and which is going to be 0.21. So you've got the speed and you've got the velocity as well. So 2 times the mass, which is 0.037, times 0.21. And since they are not moving exactly horizontal, so I need this component of the velocity, right? The horizontal component of velocity. And if I'm looking for the horizontal component of velocity, which is adjacent to theta, I must be using a cos component. So I'm just going to use cos theta over here, because I'm using 2 over there. So that is why I'm going to use cos theta over there, right? Somehow like theta. Okay. So I'm just going to work this thing down. And by solving it down, I must be having something like uh, theta. You've just got this equation. You just need to solve it down. And after solving it down, you'll be having theta is equals to 51.4 degrees. That has to be the final answer, right? You can solve it down by just using your calculator. Now, I've got this question number 13, right? And in the question number 13, a student is placing 2 magnets on the top pan balance, something like this. The student clamped the metal wire horizontally in a uniform magnetic field. He clamped the wire something like this. The length of the metal wire in the magnetic field is 40 millimeters, right? This length is going to be 40 millimeters. When the switch was closed, the reading on the ammeter was 3.1 ampere. You've got the current. You've got the reading on the balance was 0.45 G, any grams. And then you've got the length of this thingy as well. So what are you going to do? You just need to calculate the magnetic field strength, yani B, right? So we need to calculate B. And how I'm going to calculate B? I'm just going to keep the weight of this thingy, equals to the force acting on a conductor, which is ILB sine theta, right? So the weight acting on that wire must be equal to ILB sine theta. So the weight can be calculated by using the mass. You can see that the mass is 0.45 grams. That could be 0.45 times 10 raised to the power of -3 times 9.81 is equal to the current. That has to be 3.1, right? The length in that thingy is something like 40 millimeters. Would you mind me writing 40 millimeters to be something like 40 times 10 raised to the power of -3? Magnetic field strength is what we need to calculate, and sine theta has to be 1, right? So by just using this thing down, B must be equal to 0.45 times 10 raised to the power of -3 times 9.81 divided by 3.1 times 40 times 10 raised to the power of -3. So by just solving this thing down, I must be having the final magnetic flux density, and that must be 0.0356 Tesla, right? So that is how I'm going to calculate the magnetic flux density. Now, we've got the question number 14, right? The omega minus baryon was discovered in 1964 when a negative kaon meson was observed to collide with a stationary proton, right? So what is really basically happening, a negative kaon is going to collide with a proton, and after colliding with a proton, they are giving rise to the omega minus baryon. So, state the quark structure of a meson. So like baryon is made up of 3 quarks. Whenever you're being asked about the meson, remember that it is just a combination of a quark and an anti-quark, right? They're not specified about anything. They're just asking you that, you just need to talk about the meson's quark structure, right? So that must be quark plus anti-quark. You need to cram all those definitions of what is a meson, what is a baryon, what is a hadron from the book, right? Now, explain how the law of conservation of the baryon number and the law of conservation of charge are obeyed in this reaction, right? So first of all, if you're talking about the baryon number, remember that this negative cation has a baryon number. Now, this is a baryon number, right? You need to remember that table from the book as well. So the baryon number, if I'm talking about the baryon number, remember that the baryon number of this negative cation has to be 0, right? And the proton, since itself is, since proton itself is a baryon, the baryon number going to be 1. It should be equal to, what is the going to be the baryon number of omega minus? That is 1. And cation got 0, 0. So you can see that as far as the baryon number, so it is conserved on both the sides. Now, if you're talking about the next thing, you've got the charge number, right? And we need to talk about that, whether the charge remains conserved or not. So if you talk about the charges over here, you can see that the cation got a negative charge. And as far as the proton is concerned, it got a positive charge. So it would be something like negative E plus C equals to omega minus got a negative charge. And this positive cation has to be E charge. And this neutral cation, it must have a 0 charge. So you can see that everything cancels out on either side, and we've got the equal charge number on both the sides. So this equation is conserved as far as the baryon number is concerned, or as far as the charge is concerned. Now, we've got the next thing. And we've got the next thing. By its discovery, the mass of the omega minus was predicted to be 2.9714 times 10 to the power of negative 37, right? The most recent accepted value for the mass of omega minus is 1672 mega electron volts, right? 1672 mega electron volts per c square. So first of all, you need to calculate the percentage difference. If you want to calculate the percentage difference, one thing is for sure, that you're going to keep the unit same. So either convert this kilogram into mega electron volt upon c square, or convert this mega electron volt per c square into kilograms. So what I'm going to do, I'm going to convert these kilograms into mega electron volt, something like that. And how can we do that? 2.9714 times 10 to the power of negative 27, which is the mass in kilograms, right? I'm going to times it by c square. The value of c, everybody knows that 3 times 10 to the power of 8 square, right? And then I'm going to divide it by the charge on one electron, and that has to be 1.6 times 10 to the power of negative 19. And for mega, it comes out to be 10 to the power of 6. So when you'll solve everything down, you must be having 1671.4 mega electron volt per c square. Now I'm going to calculate the percentage difference between the previous and the new value. So that's going to be, you can see that the new value is 1672. So 1672 minus 1671.4 divided by 1672, right? And if you're going to calculate the percentage, okay, you just need to calculate the percentage difference. So I can give that in percentage as well. I need to give that in percentage, right? So while solving it down, you must have the final answer as 0.036%. So that is the percentage difference between the values of the mass of the omega minus in the two different eras. Now, a photograph shows the track produced by the particles in the particle detector when a negative cation collided with a stationary proton. The tracks produced K plus and omega minus are labeled. Cation, negative cation got itself into omega minus and K plus, right? So you've got, if you could just imagine, you've got neutrality on the right-hand side. And to conserve, and for this reaction to really happen, there must be a neutrality to the left as well, right? Explain how evidence from the photograph shows that neutral cation was also formed. So first of all, this is a 3-marker question. We just need to write a few points. So first of all, remember that since it has to be a neutral particle, so first of all, the first evidence is that whenever you're talking about a neutral particle like cation would not leave a single trace, right? It is not going to leave a single trace, right? And then as far as the conservation of momentum is conserved, as far as the conservation of momentum is concerned, since we have got neutrality on the right hand side, on the right side, there must be something like a neutral particle going to the left as well, right? So as per the law of conservation of momentum is concerned, as far as the law of conservation of momentum is concerned, there must be a neutral particle, there must be a neutral particle going to left, only to conserve the neutrality on the right side. Got it? Now we've got this question number 15, and in the question number 15, we have got a turntable, right? This table is going to turn, right? Like the people use it on the table. This glass gonna rotate and it's gonna serve to everyone sitting on these chairs. Rotates around the vertical axis. Dining turntables can be used on the large tables as shown, right? Mostly in Japan. So the turntable is used to move the glass of water to different positions. The photograph below shows the side view of the glass of water on the turntable. So you've got something like this, you know, you've understood all these things. The turntable is rotated through 160 degrees, right? As shown. The time taken for the turntable to be rotated 160 degrees is 2.2 seconds. But still, we do not have the time period, and we will be unable to calculate the angular velocity, which is the 2 pi upon the time period, right? So first of all, I'm going to calculate the time period. If it is taking 160 degrees to, if it is taking 2.2 seconds to cover up 160 degrees, it means that it would take it would take 2.2 upon 160 to cover up 1 degree. But I'm not concerned about 1 degree. I'm looking for the time period. So if I want to rotate it for 360 degrees, it would cover this much of time, right? So by just following this stoichiometry, I've got the time period, and that time period would be something like 4.95 seconds. And once I've got the time period, I'm just going to plug it down over here, 2 pi upon the time period, which is 4.95. And by sorting it down, I would be having the final answer for the angular velocity, which is 1.27 radians per second, right? So that is how I'm going to talk about this question. Then I've got this second part. The glass can be placed at different positions, right? Explain why the angular velocity of the glass is the same, but its velocity varies depending on the position of the glass on the turntable. So over here, first of all, it is a 2-marker question, but you need to remember one thing, that angular velocity, the direction of the angular velocity can be determined by using the right-hand rule, right? You just need to close your fingers in the direction of motion, and your thumb should be pointing towards the direction of angular velocity. So what does that mean? Wherever the object is it here, the angular velocity would always be upward, right? But if you talk about the tangential velocity, remember that it would always be tangent to the point where it is. So you can see that though the angular velocity, though the magnitude of both are going to be the same, but where angular velocity is going to change, its angular velocity is going to keep its direction same no matter where it is. The tangential velocity would be changing its direction again and again, right? So first of all, remember that whenever you talk about angular velocity only depends on the time period. It depends on the time period, right? You've got the formula 2 pi upon t, right? And as far as the tangential velocity is concerned, tangential velocity, it was v is equals to r omega, right? So it depends upon r as well. Got it? So you first of all, 2-marker question, reference to the formulas, then talk about the directions which I told you up over there, right? Just tell them that the direction of a body moving, having an angular velocity would be same all the time, right? But the velocity would keep on changing, right? Because velocity's direction in a circular path is tangent to that point. So that is how you're going to answer this question. You've got 2 points. Now, we've got something like B1, right? And in this question, they're telling us that the maximum frictional force between the glass of water and the turntable is equal to mg upon 30, right? So you've got this force, and that comes out to be mg upon 30, where m is the mass of the glass of water. Someone says that if they place the glass less than 5 centimeters from the edge of the turntable, then the glass will slide when the turntable rotates, right? If you're going to keep the glass less than 5 centimeters from the edge, meaning thereby, for example, if this is the edge, you know, if you're gonna place, this is 5 centimeter, if you're gonna place that glass right over here, and this turntable gonna rotate, the glass gonna hop down, right? Deduce whether they are correct or not. Angular velocity is given. You have got the diameter of the turntable as well, and that comes out to be somehow 50 centimeters, right? So, I'm just going to calculate the, somehow like the like the distance from which it is suitable, right? So what I'll be using a formula which is F is equals to, I'll be, using this formula which is F is equals to mv square upon r, which can also be written as m r omega square, right? So if I've got this formula, first of all, I'm just going to calculate the radii, right? And the radius comes out to be something like F upon m omega square, right? Now, as far as the force is concerned, if you're talking about this force, first of all, you need to admit that the centripetal force acting on this sort of an object should be equal to the, force acting inside the field. So what does that really mean? That mv square upon r is going to be something like mv square upon r should be equal to qvb, right? This v and this v could get cancelled out. And, if you're going to talk about something like r, that r should be mv divided by qb, right? So r comes out to be something like momentum divided by the qb, right? So you've got this formula, momentum divided by qb. And if you're really looking for the momentum, because only the momentum can give me the velocity here, so momentum has to be r times qb. R, which was 29 centimeter, meaning thereby 0.29. The charge of proton going to be 1.6 times 10 raised to the power of negative 19. The magnetic field strength is going to be 0.55, right? I'm just going to work this thing down, and that comes out to be something like 2.56 times 10 raised to the power of negative 30. And then this momentum is equal to mv, right? And once you've got this mv, since you're talking about the speed, so speed has to be 2.56 times 10 raised to the power of negative 13, sorry, negative 13, divided by the mass, and the mass going to be 1.6 times 10 raised to the power of negative 27. And now I've got 1.53 times 10 raised to the power of 7. So you can see that I've got a different speed. Initially I was having 1.75. So they're not comparable. So, they were right when they told us that the speed would not be the same, right? Now we've got this question number 17. The output of the power supply is varying, right? Output of the power supply is going to vary as shown. This is the potential difference. And over here, I've got the time. A capacitor can be connected to the power supply to modify this output. So capacitor, since everybody knows that capacitor is basically an ignition to the power, as output increases, the capacitor charges. The capacitor modifies the output and produces the variation shown by the bold line on the graph above, these bold lines, something like these, right? And somewhere you've got this original output, right? Output with the capacitor over here and output with the original output. Show that the So now they've got something like the potential difference across the capacitor at the end of the period of discharge. So capacitor, you can see that it always coming over here, right? Somehow like this. Okay. So you can see that this line basically is going till 3.5. So 3.5 has to be the voltage whenever the capacitor going to discharge, right? Whenever it's going to pulls itself back. Now, you've got this B part, and in the B part, the capacitor discharges through a resistor labeled with a value of 6.8 kilo ohms, right? You've got a resistor, which is 6.8 kilo ohms, and a tolerance of plus minus 5%. The capacitor has a capacitance of 3.3 microfarad. You've got you've got this thingy as well. And then deduce whether the output with the capacitor shown on the graph is consistent with the resistance tolerance or not. So the capacitor has a capacitance of 3.3 microfarad, and we need to deduce that whether the output with the capacitor shown on the graph is consistent with the resistance tolerance of 5 plus minus 5% or not. So basically, we're just talking about the resistance calculation. So in this question, I'll be using the main formula for the voltage during the discharging, and that was log V is equals to log V naught minus T upon RC. That is a formula I'm going to use. So if you could go back to the graph, the maximum value of voltage one can have is 5. I'm taking this as a cycle, right? 5. And you can see that it drops to, this is where the thingy discharges, and that is going to be something like 7.5 milliseconds, right? So I've got the time, and this voltage is going to be 3.5. So V log V, it is going to be log 3.5. Log V not going to be log 5 minus T 7.5 milliseconds minus 3 divided by the resistance and times the capacitance is going to be 3.3 microfarad. So I've plugged these values in. I'm going to calculate the resistance and just need to check that whether it comes into the range of tolerance or not. So I'll come up with 7.5 times 10 raised to the power of negative 3 divided by R times 3.3 10 raised to the power of negative 6 farads is equals to log 5 minus log 3.5. Is that clear? So I've got something like, 1 upon R is equals to log 5 minus log 3.5 times 3.3 times 10 raised to the power of negative 6. And I'm going to divide it by 7.5 times 10 raised to the power of minus 3. By sorting all these things down, I would be having the resistance, and that somehow comes out to be 6640 ohms. What was the original resistance I was having? That was 6800 ohms, right? With a plus minus 5% accuracy, I would be having 6800 plus minus 340. Well, 5% of 6800 would be 340. So the value should be, the minimum value is going to be 6460. And, the maximum value would be, you just need to add them down. So 6800 plus 340 is going to be something like 7140. And I've got 6640. So it is coming within the range, right? So this resistance, yes, resistance does agree, right? So that is how we're going to talk about this question. Now, I've got this question number 3, and we need to calculate the change in the energy stored in the capacitor during the discharging time, right? We need to talk about during the discharging time. So, that thing is simple. If you're going to calculate the work done, that has to be 1 by 2 C delta V square. So 1 by 2, capacitance was 3.3 microfarad, yani minus 6 farad, times the change in the velocity, the change in the voltages was 5, right, square, minus the lower voltage was 3.5 square, square over here. And when I'm going to solve it down, I must be having the energy, and that comes out to be 2.04 times 10 raised to the power of negative 5 joules, right? Now, in the third part, what I've got, the resistor is replaced with a bulb and a much lower resistance than 6.8 kilo ohms. Explain why the output is now very similar to the original output of the power supply. Well, even if you've got the new bulb or the new resistance, which is lower than this thingy, if you've got resistance lower than this thingy, the time constant has to be RC. If you're going to lower the resistance, time constant would decrease. What does that mean? That the time constant would be small. And if the time constant is small, remember that the capacitor is going to discharge much more quickly, right? So quick discharging as well, right? So we've got quick discharging as well. Okay. So these are the points, output is now very similar to the original output of the power supply. So that is why you can see that the capacitor is going to completely discharge these things, right? So yeah, that is how we're going to talk about this thing. Now we've got the next question, and that is going to be the question number 18. Some mobile phones can be charged for using a wireless charger, blah, blah, blah. This is just about the wireless charging, the provision of the alternating current in the coil. There is a second coil of the wire in the mobile phone. The diagram of the charger in the mobile phone is shown below, something like this. Explain how the mobile phone charges when placed near the charger. So you just need to mention one thing, that the current in the charger going to produce some sort of a magnetic field, right? And that magnetic field, this current is due to AC, so that magnetic field going to vary, right? And when this magnetic field would be varying, what does that mean? Through the phone, the flux gonna change, magnetic flux gonna change. And remember that whenever magnetic flux gonna change, an EMF is induced, right? And when the EMF would be induced, what does that mean? That the current would start flowing through the mobile phone, and the mobile phone would get charged back, right? So these are things that you need to remember. I've got you all the 4 points for a 4 marker. You just need to write them down casually. Now you've got the B part. A teacher demonstrated simplified version, blah, blah, blah. The flux density produced by the coil connected to the AC supply has a maximum value of 80 millitesla. You've got this maximum value of the magnetic field. Calculate the maximum magnetic flux linkage, right? You need to calculate the maximum magnetic flux linkage for the coil connected to the AC supply. You've got the diameter of the coil, and you've got the number of turns in each coil. So what I'm going to do, we're going to calculate the maximum magnetic flux linkage. It has to be N phi, and phi has to be N times BA, right? You've already got the number of coils, and these number of coils are 50. The magnetic field strength is already what we've got, 18 times 10 to the power of -3. The area of this thingy can be calculated easily by using pi d square upon 4. So d has to be 4 centimeter, which could be 0.04 square divided by 4. And you just need to now work it down, and you'll have something like 1.13 times 10 to the power of -3 Weber. That is how you're going to calculate the flux linkage. Remember that only phi is flux. If it is built up by the number of lines, then that is going to be N phi. The maximum potential difference across the coil connected to the digital voltmeter is less than the maximum potential difference of the AC supply, right? The maximum potential difference across the coil connected to the digital voltmeter is less than the maximum potential difference of the AC supply. Suggest why. So first of all, the reason behind that is that maybe the coils are too far apart, right? The distance between the coils far apart. And apart from that, you can also mention that there is no iron core joining them up, right? So that is why, they would have more than that. Now, we've got this question number 19. The diagram shows a negatively charged plate above a positively charged solar panel. And if you've got a positively charged solar panel, what you're going to do, the diagram shows, add to the diagram shows the electric field. So if this is a positive, so electric field should be from positive to the negative thingy. And explain why the sand particle move as shown. Since you have got the sand particle and you have given it a positive charge. And if you have given it a positive charge, the charge particles, that does make sense. The charge particles are going to experience some sort of force in the electric field, right? So the charge particles experiencing force in electric field, absolutely, right? And similarly, secondly, what you're going to talk about, that somehow the force on the electric field must be greater than the weight of the particle. That is why they're moving in this direction, right? Force of the electric field must be greater than the weight. Okay, that is how you can also mention. Apart from that, in the second part, show that the electric field strength between the negatively charged plate and the solar panel is about this. You've got the D and the V. So you're just going to use E is equals to V upon D. 12.2 times 10 raised to the power of 3 divided by the D. The D is going to be 1.50. So that's going to be 0.015. You're going to divide it down and you must be having 813,000 volt per meter. Got it? Now, you've got the diameter of the sand particle, the maximum positive charge that can be given to the sand particles when the solar panel is charged is this. That is a maximum charge we can have. We've got the diameter as well. Only some of these particles could be lifted from the solar panel when using an electric field strength of this one, right? Deduce the largest diameter of sand particles given in this table that could be lifted from the solar panel. And density of the sand is this. So basically what we're going to do, we just need to calculate the maximum diameter that we can pick up, right? If you want to use the maximum diameter that you can pick up, first of all, remember that the forces acting on those particles must be the electric force. F is equals to EQ. And apart from that, you've got F is equals to mg as well. Mg would be the weight, and the electric field must be upward, right? So you've got the upward force as well, and you've got the downward thingy as well. Okay. So now what you're going to do, first of all, you need to calculate the upward force, right? And if you want to calculate the upward force, what are you going to do? You just need to multiply this thingy by the charge, right? So the upward force comes out to be something like E, which is 81. Well, we've just calculated that 813,000. Okay, I'm just going to use the thing that's been given. 8.1 times 10 raised to the power of 5 times the charge. And the charge is going to be 4 times 10 raised to the power of negative 12. 4 times 10 raised to the power of negative 12. I'm just going to times them up, and I've got 3.24 times 10 raised to the power of negative 6 newtons, right? That is the upward force acting on that thingy. Now I've got the weight, right? So if I'm talking about the weight, you can already see that. Okay. Has been given in the question, and that is going to be mg upon 30, right? So you've got mg. I'm just going to plug it down over here. mg divided by 30 times m omega square. You can easily see that this m and m going to cancel out. I'm just going to calculate the radii, and that is going to be 9.81 divided by 30 times omega square, and which is going to be 1.3 square, right? I'm just going to solve it down, and I've got 0.193 as the final radii, right? But as been given that the diameter turntable is 50 centimeters, so the radius has to be 25. Got it? Centimeters. If this is in meters and you want it in centimeters as well, that would be 19.3. So the radius left out, 25 minus 19.3, comes out to 5.7, which is exactly greater than 5. So what does that mean? That the centripetal force would be effective until 5.7. After 5.7, it would keep on decreasing. So that is why they were correct. That if you're going to place it 5 cent in the 5 centimeter from the edge of the turntable, then the glass is probable to be hopped down. So that is how we're going to talk about this one. Now we have got this second part. Two identical glasses are placed at the same distance from the edge of the turntable. One of the glass is filled with water and the other is empty, right? Explain whether either of these glasses would be more likely to slide as the turntable is rotated or not. The final expression for the radius that you guys got was g upon 30 omega square. Was there anywhere mass over here? No, right? So what does that mean? Since it is not dependent, the radius is not dependent upon the mass. So what does that mean? That both the glasses would be equally likely to slide because they're not really affected by the mass. Okay. So both glasses are equally likely to be hopped down. So that is how you're going to talk about this question, right? Now, I've got the next one. And the next question is, you've got this 16th over here. The simplified diagram shows a LINAC and a cyclotron. Both machines are used to accelerate the charged particles, and explain how these machines use a potential difference to accelerate the charged particles, right? If you talk about this LINAC, it's going to get some potential over here. If you talk about the cyclotron, it's going to get you some potential over here. So we just need to talk about that how the application of the potential difference would get you to charge these particles, right? So first of all, whenever you're going to talk about it, the first thing he has to be that the potential difference applied provides an electric field, right? And if potential difference is, somehow providing you an electric field, some force must be acting on the particles. And if there is some force acting on the particles, the electric field is going to accelerate those particles, right? Electric field is going to accelerate those particles, right? Thirdly, since you've got the electric field, that electric field is going to be alternating, right? You remember the electric field is going to be alternating, so the particles would never be in a constant velocity, they would always be accelerating. So there is a component, they would always be accelerating. Is that clear? Now, after that, whenever you're going to talk about the another point, you just need to remember that the time taken between the leaving and entering the electric field in each machine is going to be the same, whether you're talking about LINAC or a cyclotron. And remember, in both the machines, the frequency of the alternating potential difference is constant as well. So since we're giving it some sort of an alternating current, it would keep on changing the magnetic field, right? It would keep on changing the electric field as well. If it keep on changing the electric field, it would keep on accelerating as well. And if it keeps on accelerating, that is what we need to answer. Only for the sake of 6 marks, I'm just gonna add on some points. Frequency would be the same. Frequency would be same, right? And fifthly, whenever you're gonna talk about it, the time of exit or entering the machine would be the same as well. So there would be some sort of a homogeneity, right? Apart from that, you can also recall that electric field in the tubes of LINAC and the cyclotron, uh, the D's would be and only for the sake of sixth point, you can just simply mention that the electric field is going to some sort of would be applied through the fields of LINAC and the D's of the cyclotron, right? That is where the electric field is applied. I've told you earlier on over here. So that is how you just need to mention. First of all, just tell them that there would be a potential difference that's going to give you electric field. Electric field going to get you some sort of a force. The force going to get you some sort of an acceleration. And that is what they've been asking, right? Okay. Now you've got this part B. And in the part B, a scientist plans to use each type of a particle accelerator to accelerate protons from rest. In LINAC, the potential difference is 0.40 megawatts is applied to the tubes. The proton pass through 4 gaps. Show that the speed of proton is about this thing as they leave the 4th gap. So what I would be doing, I would just be, calculating the total work done required when this 0.40 megavolts would be applied. And then I'll keep that work done equals to, 1 by 2 mv square. So the work done, since V is equals to W upon Q, so the work done has to be V times Q. You can see that the voltage has to be 0.40 times 10 to the power of 6. And, you've got 0.4 times 10 to the power of 6. And after that, you've got the charge. What is the charge on a proton? It has to be 1.6 times 10 to the power of negative 90. So I'm just going to times them down, and I'll be having 2.56 times 10 to the power of negative 30, right? So you need to do it like this. And after that thingy, you've got something like the work done, you're going to keep it equal to the work done. So work done has to be half mv square, and I'm going to calculate the speed. So speed has to be 2 times the work done divided by the mass, and then v comes out to be the square root of 2 times the work done divided by the mass. So I'm just going to plug the values in. 2 times the work done. Work done is going to be 2.56 times 10 to the power of negative 30 divided by the mass of the proton. If I'm not wrong, the mass of the proton will be 1.6 times 10 to the power of negative 27. And when you're going to work this thing down, the velocity would be somewhere around 2 times 10 to the power of 7, which for me is 1.75 times 10 to the power of 7 meters per second, right? That is how we're going to work out the speeds. Okay. In a cyclotron, a proton leaves the Ds when the radius of their path is 29 centimeter, right? So what does that mean? That at 29 centimeter, there is not essential centripetal force to keep the protons in that circular D. Deduce whether the speed of proton as they leave the cyclotron is the same as the speed of proton as they leave the fourth gap in the Linac. We have got the magnetic flux density, and that is going to be 0.55 over here as well, right? So first of all, what I would be doing, for the particle to be suspended, the upward force acting, which is 3.24 times 10 to the power of negative 6, it must be equal to mg. So you've got the mass, and that mass is what we need to calculate, times it by 9.81, and we're just going to work this thing down. So mass comes out to be 3.24 times 10 to the power of negative 6 divided by 9.81. So, we just need to divide them down, and the mass now comes out to be 3.30 times 10 to the power of negative 7. Once you've got the mass, with the help of density, which is something like 2600, you can calculate the volume. Density is equals to mass upon volume, so volume has to be mass upon density. Mass is 3.30 times 10 to the power of negative 7, and the diameter, which we have got, the density is 2600. So, by dividing them down, you'll get the volume, and that is 1.27 times 10 to the power of negative 10. So I'm going to plug in the formula for the 4 pi 3 pi r cube, keeping it equal to 1.27 times 10 to the power of minus 10. And while solving it down, I'll have the final radius to be 3.12 times 10 to the power of minus 4. What does that mean? That the diameter is what I can get by multiplying it by 2 would be 624 micrometers, right? That is the diameter that I would be having. Now, if I go back to the table, I've got this 310, I've got this 590, 720, right? I've got something like 624, which is somewhere around 720. So the largest sand particle that can be pulled up is going to be the 721. 970 cannot be pulled up, right? So that is how we're going to do this question. Now we have got this one, right? So, the solar panels are usually inclined at an angle theta to the horizontal. The plate moves parallel to the solar panel, something like this. Add to the diagram to show the force acting on the charged sand particle. So if you want to talk about the force acting on the charged sand particle, it is for very sure that the sand particle, you've got to the diagram, would be the force, since it has to be vertically downward force, right, acting on it. Explain how inclining the solar panel at an angle theta would improve the removal of sand particles from the solar panel. So we just need to talk about that, how inclining the solar panel at an angle theta. Well, since if you're going to incline that, the weight got two components. It would either be mg sine theta, or it is going to be mg cos theta. So when you're going to incline it down, one of them would be cancelled out, right? One of them would be cancelled out. So you're going to talk about mg cos theta. This is what you're going to get rid of. And yeah, so the weight should decrease, right? Okay. So that was from this paper, right? I've done this unit 4. I'll get back to you guys with the unit 5 as soon as possible. Thank you very much.